Welcome to Keentel Engineering. The energy transition is changing what grid reliability means. Fundamentally, the question is no longer whether we can build enough renewables. The question is whether the grid stays reliable when those renewables go quiet for days at a time in the middle of winter across an entire region. This briefing covers the engineering evidence behind resource adequacy in a decarbonizing power system, the risks, the methodology, the findings, and what grid planners need to do differently. The defining reliability risk of the 2030s has a name: Dunkelflaute. Dark, windless, weeks. It is a German term for extended periods of low wind and low solar. And it is the scenario that exposes every weakness in a high renewable grid simultaneously. The threat is not one thing going wrong. It is three at once. High demand, a cold spell electricity surge drives load to peak. Collapse in output. Wind and solar fall near zero across a wide geographic area. Import failure. Neighboring regions face the same weather pattern. The interconnection that normally provides backup is stressed too. Single-cause, short-duration outages are the old stress model. Dunkelflaute is the new one. In a simulated February stress event, renewable generation collapsed from 60 gigawatts to near zero within 48 hours. Not a gradual decline, a collapse. Dunkelflaute struck across northwestern Europe all at once. The scale of that drop is the key number. 60 gigawatts is enough generation to power tens of millions of homes. It went to near zero in less than 2 days. The implication for resource adequacy modeling is direct. Stress is no longer single cause or short duration. Any methodology that models reliability as a single bad hour or a single equipment failure is not modeling the actual risk. The 2030 stress event is multi-day, multi-cause, and geographically correlated. When a Dunkelflaute event is detected, operators face three dispatch strategies. All three produce the same total shortfall. Immediate action deploys maximum capacity as soon as stress is detected. Shorter outages, deeper early draw on reserves. Shortfall minimization holds reserves back and smooths severity across the event. Flatter, but longer outages. The mixed approach combines both based on foresight horizon and event profile, operationally the most complex. The key takeaway: strategy does not change total unserved energy. It changes the shape. Who loses power, when, and for how long. That has direct implications for demand-side flexibility design and storage dispatch logic. 5 methodological choices define this analysis. First, hourly time resolution with an April start. Keeps winter stress intact without year boundary distortion. Second, 34 years of real observed weather data, not synthetic peaks, actual historical patterns. Third, 100 outage patterns per year, producing 3,400 total simulation runs across the portfolio. Fourth, 2-day storage foresight, intentionally imperfect and conservative. Real-world operational constraints, not perfect dispatch. Fifth, LOLE. E target of 0.1 to 0.3 hours per year, a high reliability standard for average annual shortfall. Each choice was made to reflect the grid that will actually exist, not an idealized model. 3 findings every grid engineer should know. 1. Decarbonization does not mean unreliability. High renewable systems can meet the 0.1 to 0.3 hours per year LOLE target. The engineering evidence supports this directly. 2. Gas stays, for now. Approximately 10 gigawatts of dispatchable unabated gas remains through 2040 at very low run hours, essential during stress events rarely used otherwise. 3. Weather drives risk. 2 to 3 weather years out of 34 cause the majority of system stress. The system's reliability is determined by a small number of extreme years, and those years must be explicitly modeled, not averaged away. Approximately 10 gigawatts of unabated gas remains on the system by 2040. Annual run hours are very low. This is not baseload. It is standby capacity held for Dunkelflaute scenarios. 4 issues make it difficult to rely on without market intervention. Low run hours mean poor returns under current market structures. Viability is uncertain without capacity market reform. Most of the existing fleet was built before 2000. Refurbishment decisions are approaching now, and long-duration storage is the technology that could eventually fill this role, but not yet at the scale or cost needed to displace 10 gigawatts. Market design must adapt to keep this capacity available until the alternative is ready. Interconnection between regions is simultaneously one of the most valuable reliability tools available, and one of the most dangerous assumptions in resource adequacy modeling. As an asset, removing all interconnector imports substantially increases loss of load hours, and that effect grows more pronounced toward 2040 as renewables scale. Interconnection matters more in a high renewable system, not less. As a liability, cold weather stresses all regions simultaneously. When your system needs imports most, neighboring systems face the same Dunkelflaute. Imports fall precisely when they are most needed. The modeling implication is direct and non-negotiable. Use weather-conditional import estimates in stress scenarios, not average availability figures. Average availability is what you get in normal conditions. Dunkelflaute is not a normal condition. Real-world validation from a demand-side flexibility program at an industrial utility district, the program enrolled 340 megawatts across 18 industrial sites, 67 commercial facilities, 12 data centers, and 8 EV fleets. Results: 38% reduction in unserved energy during modeled winter stress events, 22% lower cost per megawatt hour versus the prior peak summer structure, 87% of committed curtailment delivered on first winter activation, above the 80% performance threshold. Two conclusions: demand-side flexibility is a quantifiable, bankable reliability resource, and data centers and EV fleets, when properly enrolled, are active grid assets that perform during the stress events that matter most. 5 questions that frame this field. What is resource adequacy? A system's ability to meet demand at all times. Now harder as weather-dependent renewables replace dispatchable generation. What is LOLE? Loss of load. Expectation average shortfall hours per year. 0.1 to 0.3 is the high reliability standard. Does decarbonization reduce reliability? No. High renewable portfolios met that target in multiple scenarios. Will gas still be needed by 2040? Likely yes. At 10 gigawatts and very low run hours, long-duration storage is the candidate to replace it. How should storage be sized? Beyond daily arbitrage, Dunkelflaute events and seasonal cycles must be modeled explicitly. Future directions, larger weather datasets, probabilistic stress framing, transmission constraints, large load modeling, and seasonal storage dispatch. Keentel covers all 5. Visit keentelengineering.com or contact@keentelengineering.com.